Welcome to this explainer, brought to you by Forge College. If you were with us for our last lesson, we were way up in the clouds, soaring through that high-level overview of Solana AI tooling. Well, I hope you enjoyed the view because today we are taking a massive, kind of humorous pivot. We are dropping straight out of the sky, putting on our hard hats, and stepping right into the gritty, greasy engine room of the Ethereum virtual machine. Yep, today is all about bytecode structure and opcode fundamentals. Just to ground ourselves for a second and establish exactly where we are currently in the Ethereum fundamentals track. More specifically, we're right in the middle of the EVM deep dive module, focused on execution and environment. Up until now, we've talked about high-level architecture, right? Things like memory, storage, and stack execution. But today, we are bridging that high-level architecture directly to the raw ones and zeros. Bytecode is the exact, unvarnished instruction stream that the EVM executes. Literally no fluff, no syntax sugar, just raw computational truth. So here is our blueprint for today. First, welcome to the engine room. Then, anatomy of an opcode. Next up, the push family rules, followed by init versus runtime code. Then we'll get into building a simple decoder. And finally, our summary and next steps. Section 1. Welcome to the engine room, bridging architecture to raw bytes. Okay, let's dive into this. Because the EVM doesn't read Solidity or Viper. It reads a raw, linear stream of bytes. It meticulously fetches, decodes, and executes this stream literally one step at a time. It is incredibly literal. If we want to understand how smart contracts actually operate at their core, we've got to learn how to read the raw bytes, exactly the way the EVM does. And to read those bytes, we need to define our two most important terms. First up, the opcode. An opcode is simply a single byte instruction. Think of opcodes as the individual single byte gears of our machine. Some gears add numbers, some move memory around. Second, we have the program counter, or PC. If our bytecode is a long linear blueprint, the program counter is the needle tracking our exact place on that blueprint. It tells the EVM, hey, we are currently looking at byte number 0. Okay, now byte number 1. Section 2. Anatomy of an opcode, reading the blueprint. So, how do these individual opcodes function deterministically to manipulate the EVM state? Well, what's really interesting about this is that every single opcode has a strict stack effect. The notation is super simple. How many 32-byte words does it consume, and how many does it push back? Take the stop opcode, byte 0x00. It takes 0 items and pushes 0. It just halts execution. But look at add, byte 0x01. It takes 2 items off the stack, adds them together, and pushes 1 result back. 2 to 1. POP takes 1 and leaves 0. DUP1 takes 1 and duplicates it, leaving 2. It's a perfectly balanced mechanical equation every single time. Section 3. The push family rules, the rule breakers. Every set of strict rules has a rebel. And here is why the push family are our rule breakers. While most opcodes are just one single byte of action, push 1 through push 32 bring their own luggage. They carry a raw data payload. The N in push N tells the program counter exactly how many immediate bytes to expect right after the opcode. So if you see a push opcode, it forces the program counter to skip ahead by 1 for the opcode itself, plus N bytes of data. Let's actually walk through this step by step with a real example. Imagine looking at this hex prefix, 0x6080604052. I know, it looks like a cat walked across a keyboard, right? But it's actually precise, deterministic poetry. Step 1, program counter is at 0. We read 0x60. That translates to push 1. Step 2, because it's push 1, we know the very next byte is immediate data. So we read PC plus 1, which is 0x80. Step 3, we advance our program counter by 2 total spots. We skip the data we just read and land safely at PC equals 2, ready for the exact next instruction. No guessing, just math. Section 4, init versus runtime code, the factory floor. All right, so we've got the micromechanics down. Now let's zoom out to the macro view of a deployment artifact. There is a massive difference between the code used to build a smart contract and the code that actually lives permanently on chain. I absolutely love using the metaphor of a factory building a machine here. When you deploy a contract, you send a blob of data. The first part of that blob is the initialization code, basically the constructor. This is the factory floor. It runs exactly once. Its entire job is to use opcodes like code copy to assemble the final product in memory and then mathematically return that final product. And the bytes that are returned? That is your runtime code. The runtime code is the finished machine. It gets stored permanently on chain and executes whenever someone interacts with a contract post-deployment. The factory gets demolished, the machine stays forever. Section 5. Building a simple decoder, your decoder in. We understand opcodes, we understand the push family, and we know our runtime boundaries. Let's transition to practical application by mapping bytes to opcodes without actually executing them. The absolutely crucial point here is establishing the logic for our decoder. First, we map known opcodes in a dictionary, mapping byte 0x00 to stop, 0xf3 to return, and so on. Second, we handle push 1 through push 32 programmatically because they follow a contiguous numeric pattern from 0x60 to 0x7f. Trust me, we don't want to hand type 32 entries. Third, we convert our hex string to a Python bytes object. This is vital because it prevents those nasty off by 1 errors when we slice the data. Finally, our main loop simply reads the current byte to decide if immediate bytes follow. If it's a push n, we slice n bytes as data and just advance the program counter. And this brilliantly illustrates what happens when you run that decoder against our cat on a keyboard hex string from earlier. Look at this beautifully clean output. Byte 0000 is push 1 0x80. Notice the next instruction isn't at 0001, it's at 0002. That's push 1 0x40. And at 0004, we hit mstore. We have easily, unambiguously traced the instruction boundaries and computed the next program counter without ever needing to spin up a real EVM. We've literally conquered the raw bytes. Section 6, Summary and Next Steps, Completing the Blueprint. We have covered a tremendous amount of ground in the engine room today. Let's lock in our key takeaways. Opcodes are 1 byte. The push family consumes n immediate bytes. Initialization code runs once to build the machine, and runtime code is the machine stored permanently on-chain. Keep those deterministic rules in your head, and you can parse literally any contract. As a quick reminder, this explainer was proudly made by Forge College. If you want to master these concepts, play with the Python decoder code we discussed, and dive deeper into other incredible Web3 topics, I highly encourage you to visit forge.college. But hey, before you go, I want to leave you with one provocative question. We know how to read the blueprint now, but what happens when these perfectly decoded instructions actually hit the EVM state? How does memory react? How does gas get calculated? Keep that in mind, and I'll see you in the next one to find out.